Hello! In this video we will do more equilibrium calculations to get better at doing them and also to learn some kind of nuanced ways that you can use them to get answers in different kinds of situations. So here's our first example. It looks very similar to ones we've done before. You have a reaction, you have an equilibrium constant at some temperature, and here we're asked to find the equilibrium concentrations of all species given the initial concentrations of the reactants. And then this implies that there's no products, right? So we know this reaction is going to go to the right because there's no nitric oxide products. And only in chemistry will we have a sentence that makes sense when you say, because no. It works for nitric oxide. So, all right, we've done this before, but the big difference here is that you have different concentrations of the reactants, and they're not the same as opposed to our previous problems. And we'll see how that affects things in a minute. So I'm going to make an icebox. The goal here is to find how X relates to the equilibrium concentrations, and then we'll plug that into the form of the equilibrium constant expression. And so, all right, we put in our initial concentrations. Again, we kind of assume based on the text of the problem that we're not starting with any nitric oxide, NO. And then our change goes to the right. Okay, we're making two NOs because the stoichiometric coefficient of 2 is there. And then we're reacting away the nitrogen and the oxygen, so those are negative. And then you evaluate this. You take the top line and the middle line, add them together, and you get the bottom line. All right, so the next thing we do with this is take the equilibrium constant expression. Remember, it's nitric oxide squared because there's a stoichiometric coefficient of 2, and when you make equilibrium constant expressions, you square it. Remember, in the icebox, this coefficient of 2 becomes still a coefficient, whereas in the equilibrium constant expression, it becomes an exponent. They are different. For good reason, but easy to mix up. Okay, so this equilibrium constant is equal to 0.10 because we just saw that as given in the problem. And then we plug all this stuff in. So the entire bottom line of the icebox gets plugged into the equilibrium constant expression. So now it's just a game of solving for X. We have this problem that we can't simplify it like we did before. Because before, when both the reactant concentrations were the same, then we could just say, oh great, it's that squared on the bottom, and then you take the square root of both sides, and then it works out much easier. But this one you can't do that because the initial concentrations are different. So we've got to use the quadratic equation. Oh, it's high school math coming back, right? So this is a second order polynomial. We want to find what the values of X are that make this whole thing work, which is the roots of this polynomial. And so we need to use the quadratic equation to figure that out. So I'm going to walk you through how to do this because it may have been a while since you did it. So we'll take this piece and then we'll start from there. Now the first thing we want to do is distribute this exponent into the 2x. So 2 squared is 4, x squared is x squared. So don't forget to also square the 2 in there, right? So we do that on the top. On the bottom, we FOIL. So this is how I learned it in school, is that you take the first two terms and you multiply them together, and then you add to that the product of the outside terms plus the product of the inside terms plus the product of the last terms. And it's called FOILing. All right, so now it's an algebra game of we need to collect all the terms, right? So we got all the x squareds together, all the x's together, and all the constants without and x together, and set that equal to 0 because you're trying to find the x values that make y equal to 0. So now we use the quadratic formula, and a refers to the coefficient in front of x squared, and then you take the negative sign with you into the quadratic formula. B is the coefficient in front of x, again take the negative sign, and c is the last coefficient there. So you plug all these into the quadratic formula, work that out, and you'll get the following x values. Okay, so now what do we do with these? Well, back to our original icebox here, is that we need to plug x into the bottom line of this, and then we can, solve for the concentrations of each thing. Now we have two values for x, and one of them makes sense, one of them doesn't. So if you look at this, this one straight away, one's negative. The nitric oxide over here, if you just plug x into here, you'll get a negative concentration, which doesn't make any sense. On occasion, it's not that easy. Both of your roots are positive. So then you just have to look at this and see what one makes sense. If your x is like 2, 0.4 minus 2 gives you a negative concentration. That doesn't work either. So sometimes you have to just kind of try both of them and see which one makes sense, which one doesn't. Remember, concentrations can never be negative. Now we just plug these in to the various pieces of the bottom line and find our concentrations at equilibrium. Cool, so now we've answered the question. Before you move on, please take the time to double check. So here's the original equation. Here's the form of the equilibrium constant expression with these values plugged in. And then we see, hey, look, this equals roughly 0.1, especially just the two sig figs, it equals 0.1. Great. And then we have thus answered the problem. Whew, okay, time to take a break. All right, I'm back. So, another example problem. And this one is where it starts to get a little weird. And I don't know, I didn't used to show these when I taught this class, and then just gave these problems to people and then wondered why nobody knew what was going on. So now I try to explicitly show a couple of these weird tricks you can do to kind of get answers when you're not given enough information. So here's one of them. So here we have this problem. Now we're using Kp and gas pressures, which honestly works just the same as concentrations did, except now we use pressures instead of molar. Like, it works just the same. All right, and now we're told the total pressure at equilibrium has some value, 2.5 atmospheres at some temperature. So what are the partial pressures of both hydrogen gas and water vapor? Well, I mean, if we're going to look at this with how we used to do it, we're not given enough information. We're only given one number. We have two reactants in the equilibrium constant expression. We don't really know what's going on. So, all right, let's work through this, though. The reaction direction is the first thing we look at, and here we have no idea. But that's okay, because we're not dealing with an initial and a change and a final. We're just dealing with the final. So you don't actually need to do an icebox for this because you don't have initial, so it doesn't really make sense. So when in doubt, write down the form of the equilibrium constant expression. All right. When we talk about pressures, we don't typically put them in square brackets because it's not a concentration, it's a pressure. So we put that in a normal parentheses and then cube it in this case because there's a 3 in front of the H2O. And then we cube the hydrogen gas as well because there's a 3 stoichiometric coefficient in front of that. Okay, now we have one equation with two variables. We can't solve for both of them. So it's time to reach into the tricks department. And while we know this, that from partial pressures, the total pressure is equal to the pressure of water vapor plus the pressure of H2. The only gases in the thing, right? I guess I forgot to say this earlier, but there's no solids in this equilibrium constant expression, so that's why they're not there. We're just dealing with the gases, which is good, because then we can talk about partial pressures is equal to the sum of both. And we know what that is. I mean, we have the total pressure. So what we're going to do is we'll use these two equations, and then there's two variables in here that we don't know, and then we'll use them together to solve. It's kind of a standard math thing, right? So since we're not used to dealing with, solving for pH2O and pH2, we're just going to turn that into X. It'll be a little easier to solve. So the pressure of water vapor is X. Now, the pressure of hydrogen gas is equal to the total pressure minus the water, because there's only two gases in this system. So we can say that as well. Okay. So now we can plug these things into here, right? So X is the partial pressure of water, so that goes in here. And then 2.5 minus X is the partial pressure of hydrogen, so that goes in here. Now, check this out. Whoever set this problem up was nice to you, and they gave you something that you could simplify easily. Because we don't have the tools to deal with third-order polynomials, at least not that we expect you to know. And okay, but hey, we can take the cube root of both sides of this. Awesome. Then the powers of 3 go away, and then we're left with this. And now it's just a game of solve for x. A little bit of algebra, right? Multiply both sides by the denominator, collect x's together, and then divide to get x by itself, and you get x is 2.5, or 2.25, sorry. Now we're almost there to answering the question. So the question asks, what are the partial pressures of both at equilibrium? Well, we found x. We decided earlier that x was water vapor. Totally arbitrary that we picked it that way, but we did. And so here's the partial pressure of water. And then, well, said the partial pressure of hydrogen is just 2.5 minus 2.25, minus x, basically. And so we get the partial pressure of hydrogen. And so in this orange box here is the answer. We found the partial pressures of both by using the equilibrium constant expression, and then the definition of partial pressures adding to a total. And we were given the total pressure. So, always good to double check, please do. We can plug these numbers back into the equilibrium constant expression, and then that's equal to 729. And that's pretty close to what our equilibrium constant was, 725. These are always going to be off a little bit due to the vagaries of rounding errors, and how that's made much worse when you cube and have exponents. It just exacerbates the problem. So this makes sense for us. It's not like we calculated negative 23 or something. We calculated something pretty close. Okay, last problem for this video. So this one, we have some solid ammonium carbamate that's decomposing into two different gases. And you're given a equilibrium total pressure, which is both of these gases together. And then you're asked to calculate what Kp is. Solve for Kp, whichever. Okay, so this is another weird one. We're given the total pressure at equilibrium, and we're not given initial values, we're not given really anything else. However, this one's worded slightly differently, because this problem implies that you started only with the solid, and then the reaction's got to go to the right, because you started with only the reactant. And so when you start, there's no pressures of anything, and when you go, you make the gas molecules in a ratio that's appropriate considering the stoichiometric coefficients. But anyway, so here's the form of the equilibrium constant expression. We're going to use this at some point. Now, again, the total pressure is the sum of the partial pressures, so we can write this down. But unlike the last problem, this isn't going to get us out of a jam. Because since we don't know the equilibrium constant, we have 3 unknowns and 2 equations, and that's not going to get us there. Well, now it's time to come up with some more tricks. So this problem's special because since you started with just the solid, well, as you make products, you're going to make carbon dioxide, and then you'll make twice as much ammonia because of that 2 in the balanced equation, right? So if you make some molecules, you'll make some carbon dioxides, you'll make twice as much ammonia. So we can write a little relationship like that. The other way to think of this is for however much ammonia you make, you divide that by 2, and you get the amount of carbon dioxide you make. And that's the same thing, except you just divide both sides of this equation by 2. Now, the little red text is a warning that this conclusion's not generally true. You can't do this kind of game normally. But we do it here because the only gaseous species are products, and those are the only things in the equilibrium constant, because it's Kp, and we just have a solid there, which doesn't go in the equilibrium constant expression. And we start with only reactants, and we know the balanced equation, so we can figure out the relative amounts of each of the products. And so that's the trick we use. We take this total pressure is equal to the sum of both partial pressures, and well, we can swap this out. We've in effect made a third equation for 3 variables, and then we can use that to do what we want to do. So we plug this third equation into the second equation, right? Because we're saying that the ammonia is equal to that. So that means we can just take this value and boop, drop it straight in for where the ammonia was. Hey, this is equal to 3 times the partial pressure of carbon dioxide. Well, we know the total pressure is equal to 0.318 atmospheres, and our total pressure is equal to 3 times the partial pressure of carbon dioxide. That's really nifty. So if we just divide this by 3, we get the partial pressure of carbon dioxide. Now, all right, the partial pressure of ammonia is twice the partial pressure of carbon dioxide, so you multiply that by 2. And right, when you make gas, if you make 3 particles of gas, one of them's carbon dioxide, 2 is ammonia, so out of your partial pressures, a third is going to come from carbon dioxide and 2/3 from ammonia. So that makes sense, actually, in a weird way. So now let's finish this out, right? Our goal is to calculate Kp, so here's Kp. We take the partial pressures of both. We're plugging basically these partial pressures back into the Kp equation, so don't forget to square the ammonia. Plug those in, and we get Kp, 4.76 times 10 to the negative 3 atmospheres cubed. And so this is yet another way to play around with equilibrium constant expressions to get information you want. it's not necessarily working in an icebox. It's instead working with the definition of partial pressure, thinking of what actually happened in the reaction and how that relates the amounts of your products together per se. Things like that to try to get more out of this theory that we're learning now. So hopefully the goal of this video was achieved, is that I'm trying to show you different things you can do with the math that we're learning here. And so hopefully it worked out, and I'll see you in class. Thank you.